Hi everyone, I'm a third-year PhD student in Earth Sciences at the University of Cambridge. I'm really looking forward to AbGradCon. The lineup seems extremely diverse, which is perfect given that the whole point of my talk is to argue in favour of interdisciplinary science. Specifically, the key questions I'm asking today are: how can we describe and integrate the complexity of naturally occurring geochemical environments into prebiotic chemistry? And can doing this help us to quantify prebiotic plausibility? Prebiotic chemistry as a field is largely concerned with discovering syntheses of those molecules that could have given rise to life. For example, holy grails in the field include nucleic acids, lipid membranes, and proteins, which I'm sure you're all aware. I would summarize prebiotic chemists as building and testing prebiotic pathways, a series of steps, reactions usually, needed to synthesize a given molecule or set of molecules. Over time, these lab-assembled pathways have become more complex. At first we had merely single-step reactions, then linear chains of reactions, and nowadays there are fully fledged systems of chemical reactions that lead to numerous desired products. A plausible prebiotic system must make use of reagents which co-occurred in early Earth environments. But it's our knowledge of the early Earth where many problems arise, because prebiotic chemists are largely reliant upon geologists for these constraints. Yet we geologists have a pretty poor understanding of the early Earth. This isn't really our fault. The first half a billion years simply have no rocks left for us to study. We do think that there was an anoxic atmosphere with surface oceans and probably some land, but we don't ultimately know how reducing that atmosphere would have been, which is very important for many types of proposed prebiotic organic chemistry. We don't know if there were continents, we don't know what the surface temperature was, and many other things. Within that global view, we have a more detailed picture of specific environments. An environment being proposed to host a particular prebiotic system is called a scenario, a testable union of chemical and geological ideas. Whilst we often talk pretty broadly about plausible environments on the early Earth, prebiotic pathways for the origin of life will have had to contend with what was actually there. Specifically, an environment is not just defined by its most interesting or useful characteristics for prebiotic chemistry. It is, in reality, a hugely diverse and dynamic system, which may pose many more challenges to the prebiotic system than any simplified lab analogue. So the challenge facing us is twofold: how to incorporate environmental complexity into the lab, and how to constrain earlier conditions sufficiently to properly evaluate prebiotic plausibility. Interinterference chemistry. This is our proposed term for describing the response of a prebiotic system to interferences that are present in the proposed host environment. Environments are bound to be defined by many species and variables external to what is strictly necessary to execute the prebiotic pathway at hand. These extra species, among many other environmental parameters, may get in the way or indeed assist with the desired reaction steps, i.e. destructively or constructively interfere with the pathway. Therefore, by thinking about interference chemistry, we can reformulate the entire problem in a way that calls upon both chemists and geologists to explore a wide reach of parameter space, not only the best conditions for a given synthesis at the paper at hand. That is to say, rather than asking if the chemicals used in our proposed prebiotic pathway have occurred anywhere on early Earth together, we can ask if a proposed prebiotic system would have survived anywhere on the early Earth. In order to demonstrate our approach, we require a toy chemical scenario that is complex enough to illustrate both the utility and present some limitations of interference chemistry, but it's simple enough to explore reasonably comprehensively. Here, we explore interference chemistry for a simple series of reactions: ribose and nucleobase formation, ribose phosphorylation, ribonucleotide formation, and ribonucleotide polymerization to make RNA. Our selected system of reactions is very close to the traditional retrosynthetic disconnection of RNA. In general, such reaction pathways are not considered to be prebiotically plausible at the present time. We do not consider our minor variation on the traditional retrosynthetic disconnection of RNA to be a novel or especially prebiotically plausible approach. However, we do choose this example because the relevant environmental dependencies have already been widely explored, which provides a perfect opportunity to illustrate how combining systems and interference chemistry may be able to formalize constraints on prebiotic plausibility. So, step 1, you take some glycoaldehyde and glyceraldehyde and react them to form ribose during simultaneous heating and base catalysis. In general, ribose is highly unstable in aqueous solution. This would be rather restrictive for any prebiotic pathway requiring ribose, and indeed the issue has plagued prebiotic chemists for some time. The presence of a borate ring moiety does improve resistance of ribose to nucleophilic attack significantly. Borate can also encourage ribose-selective forward reactions, acting as a desirable constructive interference in the reaction scheme. However, boric acid only speciates mainly as borate in aqueous solution under highly alkaline conditions. This requirement is compatible with the base catalysis we need to drive ribose formation itself, via the reaction step we describe here. However, we already have some stringent requirements here on the environmental pH. The next step is the phosphorylation of ribose to make ribose phosphate. For this step, we begin to have sufficiently quantitative constraints in place to begin formulating a model. With experimental knowledge of the reaction constant K, and some calculations we did to describe its dependence on water activity, because the forward reaction in phosphorylation involves condensation, we can plot the parameter space for expected equilibrium yield of ribose phosphate under varying conditions. On the y-axis, we have our yield of ribose phosphate. On the x-axis, we have water activity, mapped to a range of various environments. If we lose water and maintain reactant concentrations, we move along either the top or the bottom pink line. For the bottom condition, which is micromolar initial ribose and phosphate, if we residually concentrate those reactants as we lose water, we will move more steeply along the central pink line. If we account for the fact that the equilibrium constant itself actually depends on the activity of water to some extent, then equilibrium ribose phosphate increases slightly more steeply. That's the top pink line. Overall, in order to obtain greater than 1 millimolar concentrations of ribose phosphate, we are looking at some combination of reasonably high reactant concentrations and low water activity, which has more environmental implications from nature. Various combinations of equilibrium reactant concentrations are also indicated on the right-hand side. Next step, glycosylation, the reaction of nucleobase and ribose phosphate to form a nucleotide. Now, in order to stop things becoming prohibitively complex at this stage, we arbitrarily restricted sources of nucleobases in this scenario to delivery by meteorites. This imposition means we are environmentally restricted to shallow superficial environments. We followed on with our work from a model for this delivery mechanism formulated previously by Pierce et al. In their 2017 PNAS paper, but we made a few. So our results here show adenine concentration and pond volume on the y-axis and time on the x-axis. In plot A, we have totally UV shielded scenarios for the evaporative concentration of adenine in a 1 meter radius pond. Solid lines have no outflow. Dashed lines have an estimated rate of outflow, which will remove nucleobases from the pond. In plot B, we have only partial UV shielding. The orange line in plot B has only UV shielding in the wet phase, whereas the blue line shows UV shielding only in the dry phase. We find that only UV shielded systems can accumulate useful concentrations of nucleobases, peaking during the final evaporation of the pond. UV irradiation in the wet phase will destroy too many nucleobases, whereas UV irradiation in the dry phase will destroy all nucleobases. With respect to the glycosylation reaction itself, the reactant concentrations and water activity conditions required for a reaction between nucleobase and ribose phosphate are similar to the previous phosphorylation step, but less favorable. However, the experimental constraints on this step also indicate a requirement for acidic conditions, from Suarez Marina et al. In Chemical Communications. This is not a terribly compatible environmental scenario with the previous steps, which required base catalysis. This is a point I will come back to near the end of the talk. Finally, we have the polymerization of nucleic acid. We used the experimentally informed parameterization of nucleic acid polymerization by Mast et al. In their 2013 PNAS paper to explore the effect of water activity on this process. We assume that monomer-monomer addition rates depend linearly on water activity. We can only place an upper limit on polymerization efficiency because previous work used enzyme-propagated polymerization. We therefore have to assume that this will be similar to pre-activated nucleotide behavior, which is certainly a big assumption. Either way, given these assumptions, the results place constraints on the concentration convergence profile of various RNA polymer lengths. As you can see, it is a struggle to achieve long lengths under most environmentally plausible conditions. Using all of this information, we created a simple chemical network and solved for the equilibrium concentration of RNA that we would expect at different imposed initial water activities. The system is closed, which means that forward reaction will produce water due to condensation reactions, creating an inherent limit on the minimum water activity that could be achieved. Even if we adjust the plausible equilibrium constants to their most optimum values, we cannot achieve very long strands of RNA. These are far too short to code for any sorts of useful information, implying the need for some sort of open system water loss without diffusing our other reactants to access longer strands. Okay, so in my final few slides, I will try to crystallize for you all of that information into a relatively simple outcome by running quickly through an overall interference chemistry analysis of this particular system. We imposed an initial restriction that all of our nucleobases should come from meteoritic deposition, which means we need to look at restricted basins with UV shielding. Within such a basin, we universally need some way to access low water activity in order to drive all of those condensation reactions. This could involve bulk wet-dry cycles or local scale cycling in bubbles, aerosols, or protocell membranes, etc. The key is to be able to maintain reactants in one place and continuously exclude water. Fully closed systems will be incapable of producing useful results. Zooming in on these basins, we have constraints from the ribose phosphorylation step for phosphorus-rich, borate-rich, ribose-rich, alkaline restricted basins. The rock types that can host such environments are different depending on the atmospheric conditions. Specifically, under low PCO2, alkaline conditions will be possible in any given solar lake, but under high PCO2, we will need to drive alkaline conditions through serpentinizing hydrothermal systems. Glycosylation is only favored in acidic variants of these restricted basins, which provides a disconnect in the pH of these environmental scenarios. This is a fairly fundamental challenge to the scenario from the perspective of interference chemistry, because in an acidic scenario, ribose accumulation and phosphorylation will be limited. Looking at the overall path analysis, we can see that our interference chemistry approach helps to identify favored scenarios as well as places where the scenario breaks down. The most ideal is alkaline closed basins linked to mechanisms of open system water loss, but overall there is no clear prebiotically plausible scenario because even this struggles when you need acidic conditions for glycosylation. I started the talk by saying that was our expected outcome, for the prebiotic system not to be plausible. However, I hope I have convinced you that putting the environmental interferences responsible for rendering the system implausible at the front and center is a helpful way to think about the challenges we face. When I think of the limitations that I faced in mapping out the environmental parameter space for this very well studied and simple system, it seems clear to me that we need to pay closer attention to both prebiotic systems and their response to interference chemistry in the coming years. Many more variables than I considered in this talk for sure. I'm happy to take questions in the time I have left, and I'm very responsive to email if anybody has any other ideas for collaboration. Thanks for listening.